Modeling space weathering. Dan.
Thank you. Now for something completely different. I'm going to actually talk about a little science. And I guess I need to stand. Why did I just stand over here? Basically, space weathering is a pervasive. I like to walk, so I guess I'm defining the area I can pace. But what I'm interested in is the interaction of the surfaces of the space environment. And basically, there's lots of things going on because space is a very harsh environment. And so collectively, space weathering, as many of you know, is just the alterations suffered by materials when exposed to the space environment. This includes a lot of stuff. There's bombardment and vaporization by meteorites and micrometeorites, comminution, agglutination. There's crystal damage from the cosmic rays, irradiation, solar wind implantation, sputtering, lots of things. And fundamentally, what our type section is the lunar regolith. And we remote sensors look at lunar weathering, and what you see is that you generate nanophase iron amongst a bunch of other things. And essentially you take what is a beautifully diagnostic mineral absorption that you can really get a handle on and turn it into something that's dark and flat and much more challenging to analyze. And what this does is the nanophase iron is extremely optically active, and so it creates this lunar red slope. And the other effect, of course, is darkening. And it makes things very difficult to analyze remotely. But it's not just the moon that's exposed to this environment. You really have to view space weathering as the mineral's response to the energetic inputs that drive the surface away from what the mineral, the equilibrium that the mineral was formed in. And you get weathering at basically in all areas of the solar system. What's different from the moon is that you have different chemistry, different energy inputs, different situations. And so what you do is the weathering can be thought of as the result of chemical reactions in evolution that really can be understood by the underlying thermodynamic processes. And so what I look at is the chemistry. And what you can do is take the techniques and insights that are developed by materials science physics and try to assess the environment that the common asteroidal and planetary materials find themselves in, and forward model these weathering reactions. And what you get out are testable predictions about processes and products. Fundamentally, what you're looking at is a chemical environment of space, the hard vacuum, low oxygen fugacity, solar wind, hydrogen, sputtering, things like that. And you get thermal energy supplied by micrometeorite bombardment. And what you do is you just follow the chemical products. Start with olivine. Turns out that olivine is actually fairly unstable. The thermodynamics of olivine make it very susceptible to weathering. And so in a reducing environment, if you add a little bit of heat, olivines tend to lose oxygen and they're metallic cations. And what's interesting is it's the metallic cations in the M2 and M1 sites that actually produce the great absorptions that we see remotely in olivine. What happens is that these things essentially sweat out of the crystal structure and make nanophase iron. And that creates a different powerful optical component. But fundamentally, you make the olivine less optically active because what you're doing is you're taking the material out of the crystal structure that produces the fundamental absorption that is diagnostic of olivine. that ends up in the nanophase iron. We've done some experiments simulating this. Typically, olivine weathering is simulated by zapping it with lasers to simulate the micrometeorite bombardment. But what you can do is you can just put it in a reducing environment and heat the sucker up. And there's your nice olivine absorption with fresh olivine. And as you heat it up, what happens is that activates this chemical reaction. And essentially what you do is you get your lunar red slope very easily at subsolidus conditions with fairly modest energy inputs. So what you're doing is changing the chemistry and the kinetics, basically taking a reducing environment, adding a little bit of energy, and what you get is a quite lunar-like spectrum. But this is just the start. Nanophase iron is a great catalyst. And essentially what you're doing from the point of view of material science physics is you're decomposing this mineral. However you do it, what you're doing is you're essentially making this mineral more disordered, less optically active. But that's really a first stage of weathering. Because what you're doing then is you're making this nanophase iron available for other reactions. On the moon, there's not much to catalyze. Basically, you end up with a very reactive surface that chemically doesn't have any place to go because there's very little to react with. But what if you have something to react with? What I suggest is that you can get a second stage of weathering, but that depends upon a feedstock of components that can participate in the catalyzed reactions. And I think the ideal place for this is volatile-rich asteroids. You essentially create the reactive surface by decomposing olivine. And when you have volatiles available, like CO, water, ammonia, you can have a variety of catalytic reactions. And my example here is Fischer-Tropsch type, but that's just one of a range of possible catalytic reactions. And I had never heard of Fischer-Tropsch before I started looking at this. And it turns out this is an interesting reaction. It was developed characterized in Germany in the 20s. And it's basically a technology to convert hydrogen and CO into liquid hydrocarbons. And it's undergoing a minor renaissance right now because in industrial applications, you can generate liquid fuels from waste streams. In the 40s, it was used to generate liquid fuels from coal. That's what kept Germany in World War II in the last couple of years. And basically what they do is use various catalysts and vary the temperature and pressure of the reactions. And that varies your outputs. And typically what you do is get long-chain alkynes. It turns out that one of the industrial problems that you have with Fischer-Tropsch is that you get such a wide range of outputs depending on the pressure and temperature of the reaction that if you're interested in gasoline, you have to control it very carefully. Because otherwise you can get all sorts of long-chain carbons and also amino acids. If you get a little bit of ammonia in the feedstock, what you do is you produce amino acids. And this makes it interesting for volatile-rich carbonaceous chondrites because you have that feedstock available. You have the CO and the water and the ammonia. And the heat is supplied by micrometeorite bombardment. And your weathering in volatile-rich surfaces would essentially create these long-chain carbons, amino acids, and various complex organics. Regolith maturity, because as you evolve these things, what you're doing is essentially tearing apart and reassembling molecules. And so the more you weather, the more complex hydrocarbons and a wider variety of amino acids you get. And since you're basically not controlling temperature and pressure with micrometeorites, you get a huge range of temperatures and pressures. Basically, you get a correspondingly huge range of output products. So what I'm suggesting is space weathering on volatile-rich asteroids produces complex organics. This is not the only way you can produce complex organics that you find in carbonaceous chondrites, but I think that that's a reasonable source for at least some of these materials that we see in CI and CM carbonaceous chondrites. When I've given this talk to various groups, I invariably get a question of, well, this is a surface effect. How does this stuff survive atmospheric entry? Well, the thing is that asteroids are rubble piles. Basically, almost all asteroids are rubble piles, and they go through cycles of disruption and reaccretion. Impact ejecta buries surface material. You essentially invert stratigraphy all the time. And if you look at the meteorite collection, there's a fair proportion of meteorites. Something like 12% of ordinary chondrites have solar, wind, and planet gases. That is, that they've had regolith soil material that's been relithified and transported to Earth. And so you have the actual grains that used to sit on the surface of an asteroid, but they've been preserved. And so these things are samples of regolith. It's fairly straightforward to get the surface materials, relithify them, and transport them to Earth. And I could show you more pictures of gas-rich ordinary chondrites. But basically, you know, the dark stuff in these meteorites is a regolith soil, and it's mixed in with it's essentially the matrix that's gluing together these larger lithic fragments. And you see this constantly in gas-rich chondrites. So, the basic scheme can be applied to any airless body. Thermodynamics and mineral kinetics are what drive weathering. The outputs depend on the chemistry of the available inputs. Decomposition, in this sense, of common minerals can create strongly catalytic regoliths. And the range of weathering products are not going to be random. They're predictable and testable outcome of the source's mineral kinetics and chemical feedstock. And the annoying thing for a remote sensor like myself is that weathering products don't have to be optically active. Probably what happens is that most weathering products are either spectrally neutral or even suppress the object's reflected spectrum. In the case of olivine, what you're doing is you're taking the iron that makes such beautiful absorptions, and you're taking it out of the crystal structure. So since you no longer have that distorted lattice, you don't get the wonderful absorptions. For volatile-rich asteroids, then, major weathering products could include a range of carbon-rich compounds. And so the weathering in the presence of catalysts transforms this feedstock into a range of products that include long-chain carbons and amino acids. I think the interesting implication for this is that prebiotic compounds like amino acids are probably a routine byproduct of common space weathering products. Basically, any place you have an asteroid belt outside a frost line, you're going to get amino acids as a routine byproduct of space weathering, as long as you have volatile-rich asteroids, and as long as you have olivine. These are fairly common things in solar systems. So you should expect to have the precursors of life relatively abundant in any space-weathered asteroid belt. And all you need to do is accrete them to a hospitable environment. So thank you very much.
Thanks. Questions? Jeff.
Jeff Taylor, University of Hawaii. A very interesting talk, Dan. I have 2 points. One, the carbonaceous chondrites, most of them could quite possibly have been before the space weathering have all these organics. And it is important to understand what happens during the space weathering product to them. Not only could they be made in principle, but understanding that the modification by space weathering, and a preliminary look at this talk is going to be reported by Patrick Gazda in the session you're chairing. Number two, this process might be very important, what you're talking about, in lunar polar regions. If we have the raw ingredients, especially carbon from other sources, to make organics, and perhaps that's what's happened on Mercury to make those.
Oh, all right. Ed Anders did a lot of work on Fischer-Tropsch, thinking that the organics and amino acids that you found in carbonaceous chondrites were nebular formations. And it's certainly possible and probably going on. But when I talk to the chemists, they tell me that doing these kind of reactions on solid surfaces is vastly more efficient than doing them in a gas phase, like a nebula. So, I certainly don't rule out any other way of making these things. I think that this is just a possibility for a fairly efficient way of routinely making those kinds of products.
There is the third way is on the parent body during aqueous alteration.
Yeah, and that's also possible.
Okay, yes. Next.
Hi, Dan. Carl Hibbets from APL. Just a couple of process questions. Fischer-Tropsch requires some heat.
Yeah.
So in the outer solar system, is the impact velocity of micrometeoroids large enough to produce enough heat to enable these reactions?
Well, these reactions are a fairly low energy threshold. So it can either be, again, temperature and pressure vary enormously in this reaction. So if you don't have a lot of heat, you just limit your products. So yeah, it's fairly easy to make these things.
Okay. The second question isn't really process. I was struck by the olivine plot. I was looking at temperature dependency in the spectra of olivine as well. And the flexion spectra looked similar to mass spectra, messenger mass spectra of Mercury. Do you think the reason, perhaps, why we don't see a strong 1 micron bound on Mercury is simply because the surface has been heated and the olivine itself has been decomposed?
Well, I don't know how much olivine is originally on the surface of Mercury. So I think that there's a lot of things going on Mercury, including weathering in pyroxenes. And the weathering in pyroxenes is a lot more complicated than olivines. So I just showed you the simplest case, the one that I understand. When I talk to the material science theorists, what they do is they cover a whiteboard with equations and say, see, and wow, that's really cool. Actually, I was thinking about putting all these equations on one slide just to show you guys what I deal with. But the thing is that what these guys can do is make predictions on trace and minor constituents that you should see along with the nanophase iron. And that's something we're trying to work with various meteoriticists to look for those trace constituents in some of the volatile-rich meteorites. And to some extent, looking at the literature, we actually see that stuff. Whether it comes from this process or not is something that will require a lot more work.
Okay, actually, we're going to have to move on at this point. We're running late. Can we give a hand to our morning speakers, please?